Okay, so here we are with lesson number 2 in our unit on fields, and this is all about orbits. And hopefully you watched the Alice and Bob video that I posted to the classroom, and it's on the website. It's from the Perimeter Institute, and it's really, really good, and it kind of helps us with this first thought experiment. And it kind of links the notion of projectile motion and orbit. So here's a little diagram of the Earth, and the first kind of thought that we have: if we throw a baseball, it lands relatively quickly, right? So it comes back to Earth relatively quickly, and that's because of the downward force of gravity. If we fire a bullet, which has a much higher horizontal initial velocity than a baseball, the projectile will travel much farther, but eventually it will come back to Earth. So it's also affected by gravity. If we fire, say, a model rocket, and then the engine's cut off right after, so it's going really, really fast, it could travel really, really, really far. So it's a projectile too that could travel really, really, really far. But again, eventually it will come back to Earth. So the thought experiment is, what if you could fire something so fast that it never actually, its horizontal velocity was so fast that it just kind of traveled in an orbit around the Earth, and how fast would that have to be? And that is the introduction to orbit and kind of what it's all about. So hypothetically, if we can launch something fast enough, it will go around the entire world. So it'll orbit. And at a constant velocity, right, objects traveling in a circle will experience this centripetal motion. So we can determine an expression for orbital speed using expressions we already know. So here, let's start with F equals ma. And of course, the force that's acting is the force of gravity, and you can see this here. Okay? And we're talking about uniform circular motion, so we can replace a with v squared over r. Okay? If we rearrange this, we can cancel one of the r's, we can cancel the mass of the object that's in orbit, and we can solve for velocity. We'll take the square root of this, and we get that orbital velocity is the square root of g times the mass of whatever's being orbited divided by the radius that the object is orbiting at. Okay? And so this is going to set up our first problem, which is to say, hey, okay, so if we hypothetically, right at the Earth's surface, so if we went up to the 3rd floor of the school and we wanted to throw a baseball, we'll pretend that there's no air resistance. We wanted to throw a baseball, how fast would we have to throw it in order to get it to orbit the Earth? Because it would be in uniform circular motion, but it would have, as you can see, it's going to have to go pretty fast. So here's g, 6.67 times 10 to the negative 11. Here's the mass of the Earth, 5.98 times 10 to the 24th kilograms. And here's the radius of the Earth. And because we're pretty darn close to the surface, we're not going to add any height, because this is a really, really big radius. All right, so here's our expression. Now, again, we could use these numbers and just derive this, but we just derived this expression, so let's use it. We pop in our numbers, and when we do this math and then we take the square root, we get 7,908 meters per second. And yes, if you're thinking, that's almost 8 kilometers a second is how fast we would need to throw this object in order for it to orbit just above the Earth's surface, which is pretty darn quick. Okay, so probably not realistic, and we had to assume no air resistance, which of course there is, and this would be greatly affected. This object in orbit would be greatly affected by air resistance, but it's just an interesting thought. Okay, so obviously that's a really fast speed. It's one of the reasons why commercial airplanes do not ever escape the pull of gravity, right? So commercial airplanes, perhaps you've thought about this, why can't airplanes kind of, not use any fuel when they're up in the air, and just kind of go into an orbit? Well, commercial airplanes, may fly at 1,000 kilometers per hour, maybe, and that's if they're going really fast, but that's about 280 meters per second. Even the fastest commercial airplane, which was the Concorde, flew at about Mach 1.5, which is 1.5 times the speed of sound, which is about 500 meters per second. Even that comes nowhere close to 8,000 meters per second. So it's just not a reality, right? So another reason that we could never see this is that there's extreme amounts of air resistance, and this drag force, which really friction, causes really, really intense heat. So let's go up a little bit higher to something that does orbit the Earth, and that's the International Space Station. So it is typically not in the atmosphere, right? It's well above the atmosphere, and it's in a typical orbit, it's about 340 kilometers above Earth's surface. And so we want to know, okay, what's the speed of the International Space Station? Like, how fast is it traveling? And so what we'll do is we'll have to make an adjustment to our radius, because now that we're up 340 kilometers, we can't say that we're at the surface of the Earth, so we need to extend our radius, and we add the height that it is above the radius of the Earth. So we get 6.38 times 10 to the 6th plus our 3.4 times 10 to the 5th meters. So I've converted 340 kilometers into meters, and that's where this times 10 to the 5th comes from, and we get a new radius of 6.71 times 10 to the 6th. All right, so we have G, and we also know M, and so what we can do is we can sub right back in, very similar calculation to what we did before, and we'll calculate, we'll see if there's that much of a difference. So here's our numbers, we pop them in, we divide by R, take the square root, and we get 7,705 meters per second. So not that much slower. It's still going 7,700 meters per second, which is really fast in comparison to about 7.9 times 10 to the 3 meters per second at the surface of the Earth. But that space station is going really fast. When it's up there in the sky and you see it, it is moving. It doesn't look like it's moving from where we're at, but it travels really quickly. All right, so that's that. Let's talk about Kepler's laws of planetary motion. So Johann Kepler struggled with the problem of planetary motion, right? So one of the views that had been held, for a long time was that the universe traveled around, everything in the universe traveled around the sun, but in perfectly circular orbits, right? His observations, though, didn't match this view, and so really he started looking at other geometric possibilities. Eventually he tried to fit what he observed into elliptical paths, and the solutions, empirically, they matched his observations perfectly. So he was able to then formulate his 3 laws of planetary motion, and here they are. Law number 1 is that the path of each planet is an ellipse where the sun is at one focus. Okay, so with an ellipse, it has a center, of course, but very often we'll talk about the focus of an ellipse, and it has 2 of them, and it's kind of like the center of curvature of this end here and the center of curvature of this end. So the path of each planet is an ellipse, and the sun is at one focus. Now, I have drawn this ellipse to be very elliptical. Really, the motion of the planets is slightly elliptical, but close enough that most of the time we can use the equations for uniform circular motion. However, they are indeed ellipses, but they're not super elliptical as it's drawn here. They're just slightly elliptical. All right, law number 2 of Kepler's laws was that a body in orbit around another body sweeps out equal areas in equal times. So we don't have a constant velocity. So this is not in uniform circular motion because it's not uniform. The speed of the object is actually changing. But what does happen is that we sweep out an equal area in equal times. So if this area here is equal to this area here, it would do that. It would traverse that distance in an equal amount of time, which means that when the planet is farther away, it's moving a little bit slower, and when the planet is closer, it's moving a little bit faster. Okay, so the body moves fastest at its closest approach and slowest when farther away. Law number 3, and this is really interesting, is that the ratio of the radius of the orbit cubed divided by the square of the period is equal to the same constant for all planets in our solar system. Okay, so for all planets in our solar system that are moving around the sun, this ratio holds true, and that's r cubed divided by t squared, and that's equal to a constant. So we're going to use this ratio, and we're going to try and figure out example number 3. And I want you to do this. Io, a small moon of Jupiter, has an orbital radius of 4.22 times 10 to the 5th kilometers. If its period is 1.77 days, determine the mass of Jupiter. So here's something that's not orbiting the sun. It's orbiting Jupiter. And it has an orbital radius of 4.22 times 10 to the 5th. It has a period of 1.77 days. Let's find out the mass of Jupiter. So what I want you to do is I want you to try this on your own. Okay. The answer is that the mass of Jupiter is 1.9 times 10 to the 27 kilograms. But start using uniform circular motion, using Newton's laws, and develop that for uniform circular motion, and see if you can't arrive at the answer.